Hello everyone, I welcome you all to this fourth lecture session on unsteady state heat conduction. In this session, we will discuss about graphical method of solving unsteady state conduction problems. In that, we will discuss about Heisler charts, then how to use these charts, then types of graphs available to solve the unsteady state conduction problems, then finally two problems on unsteady state conduction based on graphical method. Now coming to the graphical method, that is Heisler chart method. When we have to use this graphical method or Heisler chart method, if the Biot number is greater than 0.1, then it is not possible to use lumped capacitance method. If the Biot number is less than 0.1, we can use lumped capacitance method to solve unsteady state conduction problems. In the last session, we have solved few problems on lumped capacitance method.
When the internal temperature gradient are large, lumped capacity system analysis becomes unsuitable for the analysis of transient heat conduction problems. In such situation, Heisler chart method can be implemented to determine the parameters like center line temperature, position temperature and heat transfer. With this Heisler chart, we can find out center line temperature, position temperature and heat transfer by referring different graphs. Now we will see the types of graphs which are available based on the three different infinite solids. First one plane wall, second one long cylinder and third one sphere. Here in long plane, that is infinite plane, the Biot number Bi is equal to HL by K. The thickness is 2L, L and L plus L is 2L. So Biot number Bi is HL by K and Fourier number is alpha T by L square. Here characteristic dimension for the infinite plate is L, LC as L. Remember, for the cylinder, infinite long cylinder, Biot number Bi is equal to HR0 by K and Fourier number F0 is alpha T by R0 square.
For the sphere, Biot number is HR0 by K and Fourier number F0 is equal to alpha T by R0 square. Here, one important point you have to observe. For lumped system analysis, LC is taken as L by 2 for the plate and R by 2 for cylinder, R by 3 for sphere. But here L by 2 remains same for the plate, but for the cylinder and sphere, instead of R by 2 and R by 3, here you have to take just outer radius. Please remember R0 as LC for cylinder and sphere. Now we will see the transient temperature charts for slab. Consider a slab that is a plane of thickness 2L confined to a region minus L2 plus L. The slab initially at a temperature Ti and is suddenly exposed to a convection environment having temperature T infinity with the heat transfer coefficient H on both boundary surfaces. So Biot number is given by HL by K for this slab because thickness L 2L by 2 is L. Fourier number F0 is equal to alpha T by L square. Then temperature ratio at the center Tc minus T infinity divided by Ti minus T infinity. Temperature ratio at the any position T of x comma T minus T infinity divided by Tc minus T infinity, and dimensional position x by L and dimensionless heat transfer is Q by Qi. These 6 parameters will come into picture when we are going to solve the problems on slab, where L is the half thickness of slab in meters, then x is the position in the slab, then Tc is the central line temperature. In some textbook they will use T0 as central line temperature. Tx comma T or simply T is the temperature at any position and Qi is the initial internal energy content in the slab that can be found out with the help of mCp/dt formula. Mass is rho into volume into Cp into Ti minus T infinity, that will be in joules. Then Q will be the total amount of energy lost by the plate during time T. Alpha is thermal diffusivity of the material, that is in terms of meter square per second. K is thermal conductivity of the material in watt per meter Kelvin. Now we will see the transient temperature charts for the long cylinder and sphere. Here the long cylinder and sphere are there having radius R0. Initially at a temperature Ti is suddenly subjected to convection environment with the heat transfer coefficient H and the fluid temperature T infinity. The various dimensionless parameters required for the Heisler chart solution are below. Biot number I have already told, HR0 by K, F0 alpha T by R0 square, then temperature ratio at the center. These equations are available in your data handbook. Based on the unknowns, you have to use respective graphs to solve the problems. Okay. Now we will see the main important note. I have already told in the last slide, plane wall and cylinder and sphere, if you take as a geometry, in a lumped system, the characteristic length is taken as L by 2, R by 2 for cylinder, R by 3 for sphere. In temperature chart method or graphical method, we have to use plane wall having thickness 2L in graphical method, because for infinite solids we have to use the temperature chart method to solve the problem. For infinite solid, thickness is 2L, 2L by 2 is L. For cylinder and sphere, we have to take outer radius as LC, characteristic length. Please remember this, is a very important point. First you have to calculate Biot number when the problem is given to you. If the Biot number is less than 0.1, you can go for lumped system analysis. If it is greater than 0.1, then again you have to calculate Biot number based on this formula. That means initially you have to calculate Biot number based on this LC value. If it is greater than 0.1, if you get, you have to use for a plane as L. If it is a cylinder, you have to take R0 as LC for finding Biot number. Now we will see the first problem on graphical method. A 60 mm thick large steel plate having thermal conductivity 42.6 watt per meter degree Celsius, thermal diffusivity 0.043 meter square per hour. Initially at 440 degree Celsius is suddenly exposed on both sides to an environment with the convective heat transfer coefficient 235 watt meter square degree Celsius and temperature 50 degree Celsius. Determine the center line temperature and temperature inside the plate 15 mm from the mid plane after 4.3 minutes. So here it is given 60 mm thick large steel plate. Okay, large steel plate, that means it is a large infinite solid of plate. The length is given, thickness 12, not length, sorry, it is a thickness 2L, 60 mm given, 0.06, whatever the value given is 2L. Please remember, in a large infinite solid plate, the whatever the thickness given is, you have directly take it as a 2L. 2L is equal to 60 mm, that is 0.06 meter, and thermal conductivity alpha value given, then initial temperature given Ti for 40 degree Celsius and exposed on a both sides having convective heat transfer coefficient 235 watt per meter square degree Celsius is given, then Ta, that is ambient temperature 50 degree Celsius given here, then time given 4.3 minutes. So first you have to confirm the Biot number. For that you need to find LC with the as usual method. LC is equal to 60 by 2, that is 30 mm, 0.03 meter, and Fourier number alpha T by LC square, that is 3.424. So Biot number Bi is equal to H into LC by K, that is 235 into 0.03 divided by 42.6, that is 0.165 you will get. By looking at this value, the Biot number is greater than 0.1, so it is not possible to use lumped capacitance method. The internal temperature gradients are not small, therefore internal resistance cannot be neglected. Thus, the plate cannot be considered as a lumped system. Therefore, Heisler charts can be used to find the solutions of the problem. So now we have to find center line temperature and the temperature inside the plate 15 mm from the mid plane after 4.3 minutes. So in the graphical method, actually there are three graphs are available to find the unknowns. First graph is related to temperature time history at mid plane. Second one is temperature time history at any position x, and third one heat flow. Initially we will use the first graph, that is temperature time history at a mid plane. Corresponding to the following parametric values from the Heisler chart, for the Fourier number 3.424 and Biot number 0.165, if you go to the graph, that is time history at mid plane, because we are going to find the mid plane temperature. So if you use this graph, infinite plate is the problem type. In that, temperature time history at mid plane, this graph you have to use. In that, if you observe here, Fourier number is in the x-axis and HL by K, that is nothing but Biot number. HL by K is nothing but Biot number, that is there in the graph. Then in the y-axis, T0 minus T infinity divided by Ti minus T infinity. T0 is the center line temperature that we have to find out, and T infinity will be the ambient temperature. This problem we have used as TA, and Ti is the initial temperature. So with the help of Fourier number and Biot number, we have to find out the y-axis value. Okay. Now we have the Biot number value of 0.165. If you observe the problem, Biot number we got how much? 0.165, and Fourier number as 3.424. Biot number 0.165, 0.1 is here, if you see the graphical line, and 0.2 is here. So in between 0.165 and Fourier number is 3.424. Fourier number is 3 and 4. Here 3.4, somewhere here 3.4. Okay, 3.4 and 0.165. You have to approximate. Somewhere here we will get point here to the 0.2, 0.164. So you can approximate the value as 0.6. So T0 minus T infinity divided by Ti minus T infinity value is 0.6. So here, if you see the T0 minus Ta divided by Ti minus Ta, instead of Ta in that graph they have used T infinity, the meaning one is the same, that is equal to 0.6. So we have to find out now T0 value, that is asked in the problem, the center line temperature. T0 is the center line temperature. So T0 minus 50, Ta value is given, then Ti value 450 minus 50 is equal to 0.6. Therefore T0 is equal to 284 degree Celsius. Now we have to find out temperature inside the plate 15 mm from the mid plane. That means what? It is temperature time history at any position x. The position is given 15 mm. That is why you have to use second graph of infinite plane. Second graph of infinite plane, that is here. Second graph of infinite plate, that is temperature time history at any position x. Appropriate graph you have to use. First one is temperature time history at mid plane, remember. Second one is temperature time history at any position x. Here some 15 centimeter is given, no? That means it's at any position x. In this graph, if you observe, x by L lines are 0.4, 0.5, 0.2. Then Biot number is in x-axis, and in y-axis it is T x by L minus T infinity divided by T naught minus T infinity. T x by L means temperature at any location x. Okay, these all notations are there in your data handbook. If you observe here, all the values are there. You have to go through once, then you will get the idea. What is T naught, what is Ti? All the parameters are mentioned here. T naught is central plane temperature, Ti is the initial temperature, T infinity is the fluid temperature, and T x by L temperature of the plane at any x at a time t. So now you see here x by L value if you know, and Biot number if you know, you can find out this y-axis. In this problem we know x by L value, x is 15 centimeter and L is 2L by 2, it is L. So with this value we can find out this y-axis value. So for a x by L of 0.5 and Biot number of 0.165, from the temperature time history at any position x, we get, if you go to the graph of x by L 0.5 and Biot number 0.165, you have to locate the point now. X by L is 0.5, that is here, x by L value is 0.5, line is here, okay. Then Biot number is 0.165, Biot number is 0.165 somewhere here, 0.156, 0.1 and 0.2 and 0.165, 0.165 and 0.5, 0.5 line is ending here. Approximate value you can take, it is near to 0.97 or 0.98. Approximate value you have to take, because 0.5 line is ending here and 0.165 line is somewhere here. So it is 0.97 or 0.98 you can take as a y-axis value. What is y-axis value? It is T x by L minus T infinity divided by T naught minus T infinity. Here it is, instead of T x by L, they have taken temperature T at any position x. Instead of T infinity, they have taken Ta here, and Ta minus Ta is equal to 0.97. From the graph we got y-axis value as 0.97. From this we can find out T as 276.98 degree Celsius. Now we will see example 2. A 6 mm thick stainless steel plate, density 7800 kg per meter cube, specific heat 460 joule per kg Celsius, thermal conductivity K is equal to 55 watt per meter degree Celsius, is used to form the nose section of missile. It is held initially at a uniform temperature of 30 degrees Celsius. When the missile enters the denser layers of the atmosphere at a very high velocity, the effective temperature of air surrounding the nose region attains the value of 2150 degrees Celsius. The surface convective heat transfer coefficient is estimated as 3395 watt per meter square degree Celsius. If the maximum metal temperature is not to exceed 1100 degree Celsius, determine maximum permissible time in these surroundings, and second one, inside surface temperature under these conditions. In this problem, they have not mentioned temperature at a midplane or temperature time history at any position x. We have to find out the maximum permissible time in these surroundings, that means surface. Then second one, inside surface temperature under these conditions. So the given value, 2L value given 6 mm, because it is a stainless steel plate having thickness 6 mm. Directly we have to take thickness 2L as 6 mm, 0.006 meter, density as 7800 kg per meter cube, specific heat given, thermal conductivity value given, then initial temperature is given 30 degrees Celsius, then Ta, that is a surrounding temperature 2150 degrees Celsius given, TA or T infinity. Then temperature T is given. Temperature is not to exceed 1100. This is the value of T. 1100 degrees Celsius given. We have to find out now maximum permissible time T. We have to find out time T. For that, initially we have to find out the Biot number. For that Biot number, we have to find out characteristic length, that is LC is equal to 0.006 by 2, that is 0.003. Biot number HLC by K. So you will get 0.185, which is more than 0.1. So it is not possible to use lumped capacitance method. So graphical method can be used to solve the problem. That means with the help of Heisler chart we can solve the problem. We have to find out time here. So time is there in Fourier number alpha t by LC square. Now for the surface we can take x by L equal to 1. It is there in your data handbook. For a surface you can take x by L equal to 1. It is not mentioned in the problem directly, but you should know for a surface you can take x by L equal to 1, because in this problem there is no information about the distance or midline temperature. That is why with the x by L value for a surface we can find out T minus TA and T0 minus TA value from the second graph, because for a surface x by L value equal to 1 and Biot number is equal to 0.185. If you go to the position graph, that is graph number 2 in a infinite plate, if you observe here we have the value of Biot number, that is 0.185, somewhere here 0.185, and we have the x by L value as 1, and you will get 0.93, somewhere 0.93 or 94. T minus TA divided by T0 minus TA is equal to 0.93, or T x L minus T infinity divided by T0 minus T infinity value as 0.93. With the help of this value you can find out T x by L T0 minus T infinity divided by Ti minus T infinity, because there is a formula here, T0 minus T infinity divided by Ti minus T infinity into Tx by L minus T infinity divided by T0 minus T infinity equal to T of x by L minus T infinity divided by Ti minus T infinity. In that RHS value you have all the values, and just now we have found out T minus TA divided by T0 minus TA. With the help of that you can find out this value. This will be the y-axis of the first graph. T0 minus T infinity, if you see T0 minus T infinity divided by Ti minus T infinity is the y-axis of the first graph. So if you find y-axis of the first graph, you have the Biot number, you can find out Fourier number. With the help of Fourier number you can find out time T. Again I will explain. Here in this problem we can assume for a surface x by L is equal to 1 and Biot number value we have. With the value of these two, if you go to graph number 2 in a infinite plate, you will get T minus TA divided by T0 minus TA is equal to 0.93. There is a formula in a data handbook, T minus TA divided by Ti minus TA is equal to T0 minus TA by Ti minus TA into T minus TA divided by T0 minus TA. So in this equation we have the value of left hand side, we have the value of this part, and remaining is T0 minus TA divided by Ti minus TA. This value will be the y-axis of the first graph, that is temperature midplane graph. So find out this with the help of this value. You will get as 0.495 as T0 minus TA divided by Ti minus TA. Now you go to the first graph, because you have the value of y-axis, that is T0 minus T T infinity divided by Ti minus T infinity. Okay, and Biot number you have. With the help of these two values, find out the Fourier number. So T0 minus Ta or T0 minus T infinity divided by T minus T infinity, that is 0.495, and Biot number as 0.185. 0.185 is somewhere here, 0.1 and 0.2 in between, 0.185 and 0.495, 0.495, okay, somewhere here you will get, okay, the value of Fourier number is somewhere 4.4, 4.4 or 4.5, okay, somewhere here you will get, please observe, 0.1185 and 0.495, 0.495 and 0.185, 0.185 somewhere here, that is nothing but 4.4 you can take as a Fourier number. So once you get the Fourier number, then you can easily get the time t. So Fourier number is 4.4. Fourier number is equal to alpha t by LC square. Just equate. Alpha is directly not given, but you can find out it is k by rho c. Thermal diffusivity is nothing but k by rho c, and time t is unknown. LC square equal to 4.4. Then if you substitute all the value, only time is unknown in that equation, so you will get 2.58 seconds. Now we have to find out inside surface temperature, that is T0. So you have the value of T0 minus Ta divided by Ti minus Ta as 0.495. So in this only T0 is unknown. So remaining all value you have. Ta is the ambient temperature, Ta or T infinity. Ti is the initial temperature. So find out this T0, that is as 1100 degree Celsius, 1100.6 degree Celsius. So with this I am concluding this session. So transient conduction for infinite solids, equations are available in your data handbook. Please go through once. Then different graphs of infinite plate and cylinder, and finally sphere. All graphs are available. Based on the unknown, you have to use the respective graphs to solve the unsteady heat conduction problems. The following references are used for the preparation of these slides. Thank you.